Hi students, welcome to Inside Physics. Today we are going to derive an expression for carrier concentration in semiconductors, especially in intrinsic semiconductors. See, what is carrier? In semiconductors, we know they are bipolar. The charge carriers are both electrons and holes. Here, we will calculate the concentration. Concentration is nothing but density. See, the electrons will be in conduction band as charge carriers in semiconductors, and the holes will take part in valence band as charge carriers. So, the electron density or concentration is in conduction band, and we will derive a mathematical formula for carrier concentration or electron density in a conduction band. Further, if we are given a semiconductor material which is intrinsic, that means chemically pure semiconductor material, and if you take a small volume of that material and see the number of electrons, that means the density of electrons in the conduction band of its semiconductor material, suppose if we consider it as dn, the density of electrons in the conduction band is represented by Ze. Okay, so here the another term, the probability of finding an electron in the conduction band in a particular energy state is represented by f of e. So with these functions, density function and probability function, we can write that the number of electrons in a small given volume can be written as Z of E f of E dE. So we'll start with this function and we will go further to derive the formula for electron density. So here we will see exactly what is density of electrons in a conduction band in an energy level between E and E plus dE. That means there is a small difference between E plus dE and E. This is an energy band with energy level E, and there is another energy band with energy level E plus dE. So in this energy band we are going to consider the electron density, so that we will be finding the derivation and thereby the mathematical formula. Further, see here, first of all, what is Z of E? So the electron density in quantum mechanics, we already derived that the carrier concentration will be so we can start with the electron density Z of E with this mathematical form. So h bar 2me, effective mass of electron. This is the energy level we are taking, in which we are going to find the electron density. Okay, so here if we consider the kinetic energy, this means, see, in the conduction band the electrons will be continuously moving throughout the material. So the kinetic energy is considered as E is equal to E minus EC. So this is the kinetic energy, and EC is the potential energy of the electron in the particular energy state at rest. Potential energy, EC is potential energy of the electron at rest. E is the kinetic energy. So if we can substitute E value in this form, we will get D. So this is the expression for electron density. Okay, so in the conduction band generally the lower level is having the lowest energy, and if you go further above the level, so if you consider this as conduction band, if you go upwards the energy level will be increasing. We consider the lowest level as EC, and the upper level we will generally consider as infinity. So the energy varies from EC. Generally electron, potential energy of electron at rest, and thereby moving upwards towards the upper mark of the energy, the upper limit will be taken as infinity, EC to infinity. So this is the conduction band, and the energy levels vary from lower energy level to upper energy level. Okay, so in that way we can have the limits. So this is Z of E, and I have already written what is the number of electrons in small volume of the material, Z of E F of E dE. So we already got the mathematical form for Z of E, and now the probability function of finding an electron in the conduction band can be written as F of E is equal to 1 by exponential form of okay. So this is the mathematical form of probability of finding the electron in the conduction band. So if we can take these two functions, and if we integrate this function in the limits between EC and infinity, already we have discussed about these limits. So these two functions are integrated between the limits, and thereby we will get the solution of that integration, and we can get the total number of electrons in the particular conduction band. So if you observe here, see, if the available electrons in the conduction band is very less compared to the available energy levels, we can write E minus EF far greater than 3 kT. As per Boltzmann function, this is the Boltzmann constant, this is the absolute temperature of the material. So EF is the Fermi energy level. E minus EF, this function is far greater than 3 kT when the available electrons is very less compared to the available energy levels. The number of electrons occupied, if it is very less compared to the available energy levels, we can write this function as greater than 3 kT. Okay, then this Fermi-Dirac function now can be written as Boltzmann function. Okay, now this Fermi-Dirac function can be written into the form of Boltzmann function. Okay, so if you observe, we have got the representation for density and probability. Now we integrate these two in the limits EC to infinity, because the lower conduction band limit is EC, the upper limit will be infinity. Now we proceed to integrate to get the number of electrons in the density. So now with this mathematical form we can write n is equal to, between the limits EC to infinity. Okay, what is Z of E here? 4 by h cube 2m e power 3 by 2 e minus EC whole power 1 by 2, and look at this f of E, you can write this expression. Okay, so exponential minus of E minus EF by KT. Okay, so now we can get the integration, and we will get the solution for that integral form which is taken in the limits EC to infinity. Okay, now I will write this in the form of okay, see, I will write this one as EF minus EC to E minus of E minus EC by KT. Just a minute. So look at this. This exponential form I have written in this way. If you observe, this can be taken into the form of this one again. If you observe EF minus EC, and the same, if you add these two terms as the exponential powers, you will get the same thing here. So I have just written this form into this form for my convenience to get the solution of this integration. Okay, now this is for the total integration between the limits. Okay, now I will take the forms which will be integrable, and I will take the non-integrable forms outside the integration. So this I can write this total form as look at this. I have taken this term out, and I have taken this term out of the integral, and the terms which are integrable I will be bringing into the integration. Okay, okay, see here, if you observe this integration, and we can get the solution for integration. This is in the form of, if you take E minus EC as x, e to the power of minus ax into dx, we can get this integration form as another integral form, and we can get the solution of that. See, for this particular integration form, I will write this as, okay, this term, this is the term that will be remaining the same. I am writing the solution, and this integral is changed to, can write this particular integral form can be written as x power 1 by 2. This I have taken as x, e power minus ax, e power minus this one as ax into dx. Okay, see here, a is nothing but 1 by kt, and I have taken x is equal to e minus ec. These are the two terms. I am rewritten these integral form into this one. Okay, so here if you observe, see, just okay, this integral is rewritten in the form of the x component. So if you observe this one as a solution, we can write the solution for this integral as root pi by 2a root a. Okay, see, this is the solution of this integral form, and we can get this solution in the mathematical science, and you already, I think you have already derived these solutions and for these kind of integral forms. Okay, so if you observe the whole thing here, in the entire form of this integral, we can substitute this solution. Okay, so we'll move to the first step. We'll erase the first step and we'll arrange the integral form here. See, we can write n is equal to, see, this is the term that will remain same, which is not taken part in the integration. Me here is effective mass of electron, Ef is Fermi energy, Ec is potential energy of the electron at rest. Okay, and this Ef minus Ec, I will write this in the form of Ec minus Ef. I can write it, right? Ef minus Ec, I have written minus Ec minus Ef by kT. And here if you observe, see, this integration form is taken as a solution, and here can write root pi by 2a. What is a here? 1 by kT. So if you take a as 1 by kT and root a as 1 by root of kT, okay, this is the form which we have taken. This entire integral is taken into this form. So we'll go step by step. You concentrate on the each step, how I am getting slowly into the final derivation. So if you observe, this is root pi and kT into root of kT, you can get this as kT to the power of 3 by 2. Okay, so this term goes and to the numerator, and we can write as kT to the power of 3 by 2. Kt to the power of 1, kt to the power of 1 by 2, total we have taken kt to the power of 3 by 2. This is in the denominator and it has gone to the numerator and has taken this form, kt to the power of 3 by 2. So with the help of next step, we will this integration will take a form by rearranging these terms. See, I will write here 2 pi into, see, me, this is power 3 by 2, okay, into kt, okay. See, pi root pi will become a power of 3 by 2, me to the power of 3 by 2 by h bar square. You can write h bar square. So if you observe these things, and this whole term can be written as 3 by 2. Okay. So here this one, so we'll check once again whether this is gone in a correct form. See, pi into root pi has become 3 by 2 m of e power to the power of 3 by 2. Kt is already in the power of 3 by 2. So h bar, if you multiply this with 3 by 2, it will become h bar cube. Okay. So here, see, this 2 will be multiplied by this term, and if it comes into the power of 3 by 2, what happens? 2 pi, and this is 4 pi. Okay, 4 pi, and this term will be multiplied by 3 by 2. Okay, so this is the mathematical form which we have arrived, and this is the electron density. Now see, if this total term is taken as NC, so that the total expression can be written as this one. Okay, see, NC, this total constant is taken as NC. This is the carrier concentration, number of electrons present in an energy level in a conduction band. Okay, this is Fermi energy level. This is the potential energy at rest for an electron. Okay, this is the form of carrier concentration. Okay, see, the number of electrons is directly dependent on Fermi energy level, and the term Nc, which is consisting of the forms terms mass of effective mass of electron and Boltzmann constant. Okay, so in this way we have derived an expression for the electron density in an intrinsic semiconductor. This is also called carrier concentration, as the electrons and holes are the carriers in semiconductors. Okay, in the next session we will calculate the hole density, as the holes are also one of the charge carriers. Okay, thank you.